do we know it wasn't convergent?
Well, there is a lot of convergent evolution that happens. So that's what happens in Australia, is you get a lot of convergent evolution occurring. So your sugar glider, your flying squirrel, they've converged onto they occupy the similar habitat, so they look alike. They're not related at all, not close at all. Sugar glider is much closer related to Tasmanian wolves or kangaroos or anything else in Australia than it is to anything in North America. So yeah, we'll go through convergent evolution. There's a lot of good examples of convergent evolution. Okay, so some of the geographic evidence. You have a lot of species that have both either a southern distribution or a northern distribution. We have lots of, we'll look at these southern ones first. The galaxoids are a type of fish that occur in southern Australia, southern South America, southern Africa. The carabidales, similar pattern. There are plant examples, there are animal examples. These are your African clawed frogs. Some of you probably had one of these as a pet when you were growing up. No? Yes. But you can buy these at Petland for a couple of bucks. They make terrible pets. They just sit on the bottom of the aquarium like this and wave their hands, wave food in their mouth. That's pretty much all they do. Foul water. These are lungfish. Lungfish have a South America, Africa, Australia distribution. There's lots of interesting, the Mississippi River and the Yangtze River in China have some very interesting faunal similarities. So paddlefish, for example. We have paddlefish in our Mississippi River system. There is a paddlefish species that also occurs in the Yangtze and Yellow River system in China. We have a giant salamander, the hellbender, that occurs in the eastern United States. There is a Chinese water dog that occurs in the upper reaches of the Yangtze River. They're the two species of ancient giant salamanders that are left. They're kind of a relic of times past. So many faunal similarities. We have sculpins in North America, in the northern states. It also occurs in northern Europe. Russia, they have sculpins too, a little benthic fish that lives in very cold water. So it occurs like in upper Michigan, upper Ohio, Canada. Here's Janie's example of convergent evolution. So you have here you have a marsupial anteater and an anteater, a mole. There's a marsupial mole, mouse, marsupial mouse. Everything in this, here's our flying squirrel and our sugar glider. Everything in this side is more closely related to something else on this side than it is to its counterpart in here. Australia, again, broke off very early. It only has marsupials. And these marsupials, they're occupying the flying squirrel and the sugar glider occupy similar habitats. And so they've converged on a similar body. We can look at the distribution of tectonic plates. Here's our North American plate. This is why California might fall through the ocean at some point. There are minor plates as well. There's a minor plate that runs through from Missouri to Oklahoma. These are just the major plates. There's so many islands. We talked about islands and island formation. There's so many islands in the Pacific because of all of these different fault lines. You have a lot of what are called triple junctions, and these are highly unstable triple junctions, and so you have lots of volcanic activity. This is where Godzilla's from. This is what generates tsunamis. This is what forms these islands. Most of these islands in the Pacific are volcanic in nature. So Hawaii is basically a collection of active volcanoes. If you go, the soil in Hawaii is all volcanic soil, some of it's really black. And there you can see smoldering semi-active volcanoes in the Hawaiian Islands. And in most of these islands you can as well.
So where's the Bermuda Triangle?
The Bermuda Triangle is right in here. So what you have in the Bermuda Triangle, it's a very deep, there's a very deep shelf in the Bermuda Triangle. And it's right around 30 degrees. It's right around the horse latitudes. So there's probably not aliens underwater in the Bermuda Triangle. It's probably the weird, it's a really deep shelf and then it comes up abruptly. And then it's right at the horse latitudes. You have some weird, it's very difficult to, your boat can kind of stall out in that area. And there's a lot of tropical storms in the Bermuda Triangle, or in the Bermuda as well. I mean, anytime there's a hurricane, it always goes through Bermuda, almost always coming out of the Atlantic Ocean. Sometimes they go up the Gulf, sometimes they go up the Atlantic, but they almost always hit Bermuda in that area. So maybe there's an alien underwater. I think there's more likely an alien underwater at the Bermuda Triangle than there is Bigfoot. Or Loch Ness Monster. All right, so the northern half, Laurasia, the southern half, Gondwanaland. Pangaea was not together for very long. Its formation in the Permian resulted in a mass extinction event. So Pangaea starts to break up in the early Jurassic about 180 million years ago. I'm going to go back. So the formation of the Permian is only about 225 million years ago. When I say it wasn't together for very long, it was together for about 25 to 30 million years approximately. Laurasia stays together until the mid-Cretaceous, which puts it at about 100 million years ago. It was disconnected only for about 25 million years, and then the Bering Straits forms a connection between Asia and North America. And this persisted for a long time, until the last glacial age, really. And we're going to see that's an important connection both from mammals and for humans. Green was not seen. Smells really bad. Gondwanaland starts breaking up earlier than Laurasia, so about 180 million years ago. As soon as Pangaea breaks up, basically Gondwana starts to break apart. Madagascar and India, about 130 million years. By 125 million years, You have 4 land masses in the south. You have South America, Africa, Madagascar, and India sitting out into the Indian Ocean. And then Antarctica, Australia, and New Zealand is connected together. They're the first to break up. I didn't put that on here, but I'm not making note that Antarctica, Australia, and New Zealand, their breakup is about 180 million years ago. They're the first to separate.
So they broke right when?
As soon as Pangea breaks up, Australia and New Zealand and Antarctica break off right away. And then the rest of them are together for about 50 million years, and Madagascar and India break off. And then South America and Africa break apart mostly at around 125 million years ago. At about 100 million years ago, Australia and New Zealand drift away from Antarctica. Antarctica then begins its drift down to the southern pole. At about 60 million years ago, India and Madagascar separate. India collides with Eurasia, keeps moving and collides with Eurasia. When India collides with Eurasia, it buckles the continental shelf there and forms the Himalayan mountains. I'll slow down. Drinking too much tea. This tea with raspberries making me too heavy.
So, bump Antarctica, Australia, New Zealand, back up above Madagascar.
Okay.
Then
So,
Madagascar,
yeah.
then South America after.
all right, so let's just put it here. So 180, you have Australia, New Zealand, and Antarctica separate. I'm just going to put it in a timeline. And then 130 million years ago, Madagascar and India separate. And then 100 million years ago, Australia and New Zealand separate from Antarctica. And then 60 million years ago, India and Madagascar separate. Yes, sorry. So in 125 million years ago, Africa and South America. So,
would that be a good short answer question? Or,
this is approaching an essay question.
yeah.
You guys are getting the hang of this. Because we're not done. We still have to form the Caribbean, we still have to deal with North and South America joining. The geology nerds usually like this kind of material. Because then once we build this foundation, this geological foundation of the continent's moving, then we can start draping dinosaurs and mammals on top of that. And you really need this background to understand paleontology in any detail. So that's why we're spending so much time on the Earth's geological history. Because I bet you guys have never had this level of detail of geology in any class that you've ever taken. Most people haven't, so They don't teach geology in high school. Probably the best thing you had was an 8th grade earth science class. You might have learned about seasons and some of the stuff I talked about in the previous lecture, but I promise you, your 8th grade earth science does not go through the Pangea breakup and the movement of continents.
It was 90% of your science teachers will not get that.
It'd be worse than 8th grade in middle school. Well, and the best evidence of the movement of these continents is evolution.
Right.
So you almost have to teach evolution side by side with geological history. Otherwise, it looks like you're just guessing about this, sort of taking a jigsaw puzzle apart. You really need that evolutionary information based on genetics, based on fossil reconstruction, and then this starts to make sense. Okay, let's wait on the Americas. I know I have 2 or 3 students waiting on me right now in my office, so the Americas are going to take 15 or 20 minutes to get through. I don't want to start in the middle of it. And so we'll stop here. We've gotten this far. We'll get the Americas next time, and then we'll start draping evolution and fossil record on top of this background now that we have in geological history. Do yourself a favor and go ahead and memorize that geological timetable, because it's going to become important as we start going through the evolution of different groups and when things happen.